We got his.
Ow!
Are you okay?
Yeah. Can you teach me how to flip?
To the bounce lab.
Welcome to the Bounce Lab.
Firstly, we need to find out how a trampoline propels you up into the air and why normal ground doesn't.
So we will show you the inner workings and the physics of a trampoline.
When you jump on a trampoline, you exert an upward velocity and propel yourself upwards, therefore increasing your height. Then you stop momentarily at the peak. Then change direction and begin to fall due to the gravitational force. This is called free fall. While I'm going down, the force that pulls me down is negative 9.81 meters per second squared.
To understand the forces and energy of trampolines, you must use the formula. Potential energy equals mass times gravity times height.
This is the potential energy due to gravity. People with greater masses have a greater potential energy due to gravity if they are the same height as someone with a smaller mass.
It is harder for people with greater masses to reach the same heights as people with smaller masses because gravity is pulling down harder on them.
Also, the formula force equals mass times acceleration, which is Newton's second law of motion, explains that larger masses let the spring stretch more. When the mass increases, so does the force of gravity.
Mass is usually too heavy for a spring if you just stand there, which is why you don't move unless you start to jump. As soon as Kara lands again on the trampoline, it actively adds to the upward velocity due to the springs having been stretched from the kinetic energy that's been exerted. Hooke's law is applied. Where are the springs on a trampoline? Oh, let us show you.
This is the spring.
What's Hooke's law?
Well, Hooke's law was invented by Robert Hooke, who was a 17th century physicist who studied the actions and reactions of elastic properties.
He states that the force needed to extend or compress a spring by some distance scales linearly with respect to that distance. This means that depending on the force you exert on the spring, you will receive the same distance or length of pushback return. Force equals kx, which is Hooke's law. K is the spring constant measured in newtons per meter, and x is the distance of spring, which is stretched from its equilibrium position in meters.
The harder you jump, the higher you bounce.
This is similar to Newton's third law, which I am sure you know. However, Hooke's law is concerned with the response of elastic objects, and theory is contingent on the stiffness of the spring, the K in the equation.
If the spring is stiff, there won't be much pushback. Hooke's theory has a limit of how much energy can be applied to an elastic body. So if you bounce too hard, you could potentially break the springs.
We use the formula F equals kx to find the force of spring, which is the constant multiplied by the change in spring's length. That is just how the physics behind the trampoline works. Now we will show you the physics behind doing a flip.
When you do a flip, you swing your arms to gain angular momentum before you jump. Angular momentum is very similar to normal momentum, but instead of being the product of mass and velocity, it is the product of rotational mass and angular velocity.
The rotational mass, usually called the moment of inertia, depends on both the mass of the person and how the mass is distributed. When you're in the air, you pull your legs in close to your body as it decreases your moment of inertia, so that your angular velocity increases. That means you need to use less force to spin yourself faster.
Now why does this happen?
Well, it's because of the law called the conservation of angular momentum. The conservation of angular momentum explains the angular acceleration when a person who flips brings their legs closer to the vertical axis of rotation. If the net torque is zero, the angular momentum is constant or conserved.
What is torque?
Torque is the twisting force that tends to cause rotation. Finally, you need to jump high in order to give yourself enough time to land back on your feet.
Oh yeah.
First, hey.
It's not hard.
You want me to zoom in
People
more?
with greater masses.
Guys, let me...
Okay, Nick,
Nick, cut it.
no, cut.
Wait, we should film...
Ben,
Why are you laughing?
guys,
We got history. Got me feeling the nostalgia when you look at me. Thinking about what could've happened. No